This is lecture 12 for chapter 1. This is the final lecture in this chapter, and in this lecture I'll derive the equations and find the solution for draining fluids from tanks under gravity. To derive the equation, we start by finding the rate at which a fluid is draining from the tank, and that will depend on two things. It will depend on the fluid level inside the tank and on Torricelli's law. So putting those together, we will end up with a differential equation, and from that we can construct an initial value problem. The differential equation is separable, and we will solve it using the method of separation of variables. So first we have to derive Torricelli's law. Okay, the situation we're considering is this. We have some kind of a tank, and we put a hole in it. Now the height that we'll talk about is going to be the height above the outlet hole, because any fluid that's down here, this outlet pipe can't drain. So this is really the height. But for simplicity, we'll just put this at the bottom of the pipe so that H of T is the fluid in the whole tank. Okay. But you can see that it'll only drain to where the outlet pipe is. Right, this is going to be a circular outlet pipe. It'll have a radius of R. Now this would just be the very basic situation. There are many other terms that we can consider besides the ones I'm going to write here. We could consider viscosity. We could consider that the tank itself is moving, but we won't do that. We'll just start here and say that the potential energy in the tank of the fluid of height h is mass times acceleration due to gravity times h. And the kinetic energy is 1/2 mv squared, and that's flowing out through this pipe. Okay, now equating these, we have 1/2 mv squared equals mgh, and we can solve for velocity. It's going to be square root of 2g times the square root of h. I'm writing, it's actually like this if you want to, but I'm separating out the square root of h for reasons that will become clear in a few minutes. Now what we're looking for is the flow. So the flow is going to be the velocity times the cross-sectional area. Right, so we need flow, which will be the change in volume. The time will be the velocity times that cross-sectional area, which in this case would be pi r squared, because this is a circular pipe. So that becomes pi r squared square root of 2g times the square root of h. So here's that result typed up, so you don't have to always look at my handwriting. And now we have the flow that's coming out to the outlet pipe, and we're going to equate that to the volume inside, the change of volume inside the tank, and that will depend on the geometry of the tank. So we're going to look at a cylindrical tank. You could do a conical tank or any other geometry. Just take some different steps, that's all. So here's this cylindrical tank, poorly drawn as usual. It's going to have a radius, and the radius is going to be RT, T for tank. So the volume of the fluid in the tank is pi RT squared times the fluid level H. So dV by dt is pi RT squared. And we're not going to be pushing on the sides of the tank. We're just going to be letting the fluid flow out. So the only change here is going to be in the height of the fluid inside the tank. It starts at H at times 0, and it's going to drain out. Here's the outlet. Now this change is negative. I'm going to put a negative sign here. Well, actually, I'll do that in a minute. Okay, I'm going to equate this with the results I have from Torricelli's law for this outlet pipe. So we have pi RT squared dH by dt equals pi r squared for the outlet pipe 2g and then square root of h, and it's leaving, so I'm going to put a negative sign here. All right. As you can see, this is a differential equation in terms of the height of the fluid inside the tank. I can write it like this: dH by dt equals negative, could be r for RT squared, square root of 2g times the square root of h. Now, all of these terms right here, these are just constants, and I don't want to have to write them over and over again, so I will not set them equal to 1. Instead, I will just replace them with a letter. I'll say alpha root h. Now that's my differential equation. For the initial value problem, we need an initial condition, and the initial condition is that at time 0, the height of the fluid is h naught. So now we'll find the solution, and let's look again at the form for differential equations that are separable. So in general, we would have dy by dt equals some function of y times some function of t, and of course any of these could be constants. But the idea is that they are multiplied. The function of y is multiplied by the function of t. So looking at this equation, we have the alpha, and we have the square root of h. So the square root of h is this, and all the other stuff becomes the function of t. Okay, so this is separable. I'm going to go ahead and separate the variables now. I'll put the square root of h on the other side, so I'll have h to the minus 1/2 dh. I'll be integrating that, equals negative alpha dt, and the condition is that h cannot be 0. Also notice that h has to be greater, strictly greater than 0, because it appears as under a square root, and that only makes sense because h equal to 0 would mean that the fluid is right at the level of the outlet, which isn't going to be much of a problem, or if h is less than 0, the fluid is down below it, so physically those are not restrictions. So let me go ahead and integrate both sides. This will end up being 2 square root of h equals minus alpha t plus some constant c. Now it might seem that one would want to put everything on one side and take the square root before finding c, but actually it's easier to find a c in terms of the initial condition with the equation in this form. So let's set t equal to 0. Remember, our initial condition was h at time 0 equals h naught. Okay, so I'll just substitute that into the equation. So I have 2 h naught to the 1/2 equals, now minus alpha times 0, so there's c right there. Okay, you also don't need the 2. The 2 is a constant. Remember, in the method for using an integrating factor, all kinds of terms were always combined. We're going to do the same thing here, right? We have here that, let me write this again. So we've got 2 h naught to the 1/2 equals c. So c over 2 equals h naught to the 1/2. C over 2 is a constant, just like c is a constant, so we just call this c, h naught to the 1/2. Alright, so now let's write our solution here, and before we had, I'll put the 2 on the other side, h of t to the 1/2 power equals negative alpha over 2 times t plus c, and the c was h naught to the 1/2. So now I can square everything, and I now have h of t equals the square root of the initial height inside the tank minus alpha over 2t squared. And in this case, alpha is going to be the square root of 2 times acceleration due to gravity times r over RT squared, where R is the outlet radius, the outlet pipe radius, and RT is the radius of the tank. So here's everything written nicely. Here was the initial value problem. Here was the differential equation that we're trying to solve. Here was the initial condition. We solved it by separation of variables, and we ended up with the solution, and alpha was just a placeholder for a group of constants. Now what the solution is often used to do is to find the time at which the fluid is at a certain level. It's draining out, you want to know what time is half the fluid gone, or at what time is it all gone. In other words, when it's in an empty tank. So you can solve this, just rearrange this equation for solving for T. And here's what you get for T. T equals the difference in the square roots between the initial height and the current height divided by alpha over 2. And if you want to find the time which the tank is completely emptied, that would be h of t is 0. That simplifies to this, square root of h naught divided by alpha over 2. Notice some things about this solution. In the previous cases, we had linear equations, and in these linear equations we ended up with solutions that had a steady state term and a transient term, the transients approaching asymptotically to the steady state term, which was the equilibrium value. We're not seeing that in this case. We don't have a transient term and a steady state term, and the reason for that is that this is a nonlinear problem, and the nonlinear problems end up with solutions that are very different from linear problems. Just wanted to point that out. So now we'll put some numbers to these solutions and do an example. Let's say we have some kind of an agricultural feeding tank. It's full of water, located somewhere in Montana perhaps, and this is the size of it, and a 2-inch diameter hole gets punched near the bottom of the tank, or in the bottom of the tank, and the question is, how does the fluid drain out, or how long does it take for all the fluid in this tank to drain? So I'm going to go ahead and convert all the important dimensions to meters. So here's the radius of the tank, I need the initial height, and I need the outlet. And again, this is on Earth, so here's the acceleration due to gravity as in meters per second squared. I can plug these numbers into that solution and see what Okay, now we're going to substitute these numbers into the equations. If you have one of the earlier versions of the written lecture, you will find out that there are different numbers and they aren't consistent with what I'm doing here. They're not terribly different, but they're not consistent. It has to do with me modifying problems and modifying them in one section and not carrying all the modifications through to the others. So this is an ongoing issue, and unfortunately I cannot find errors until they're proofread, or sometimes when I make a video of them, and then I can go back and correct the written lectures. So I apologize for the errors, and I welcome any that you point any of them when you point any of them out to me. Okay, so we're going to do this problem hopefully with the correct numbers. So we're starting here with the solution that we derived previously, which is correct, and we have the value for alpha right here. Now we take the numbers from the other side, substitute those into alpha, and we have a value for alpha. Then we can plug the square naught of the height of the fluid, which was 41 inches initially, into the equation and take that square root, and then we of course divide alpha by 2, and here's what we get for the height, and that can be plotted. Again, you'll see it's not the typical linear problem. If you remember, in linear problems, a steady state solution was reached asymptotically. Here the value of 0 is going to be reached exactly, and that will happen when the fluid is all drained from the tank. So substituting these into the expression for T for the time at which the fluid is drained out into the tank, we come up with about 9 minutes. Then all that fluid is drained out of the tank, and we have a plot of that in the next slide. So we start here with the fluid at some initial height, and then it drains out and it actually will reach 0, and then we stop the calculation because at that point the conditions no longer apply.